So we've covered the theory behind power series. What I'm going to do in this video, I'm going to give you a couple of examples of questions for it. I want you to read the questions, pause the video, have a crack at them and come back and check you're working against what I show you here. So here you go. First thing, I've given you a power series here. I want you to find the sum to infinity and identify the values of x for which it exists. And then the same sort of thing here for this one. I've just given you a different power series. So pause the video and have a crack at these. So the first one here, I've got the series equals 2 plus 6x plus 10x squared plus 14x cubed, so on, with the generic term being given by that. So same as before, first thing to do is look at the coefficients here. Well, for each of these coefficients, what I'm doing is I'm adding 4 on every single time. So again, it's a linear recurrence relation where I can say that un plus 1 is equal to un plus 4, with my first term u1 being given by 2. So I'm going to stick to the similar method and technique as I showed you in the video before. So I'm going to rewrite it out just so I've got it to work with. So s equals 2 plus 6x plus 10x squared plus 14x cubed, and then that would continue on. And then I'm going to take it and I'm going to multiply it by x. So I'm going to multiply it and calculate xs, which in this case is going to be given by 2x plus 6x squared plus 10x cubed, and that's going to continue on and on and on. And then again, if I label them 1 and 2, what I'm going to do, series 1, take away series 2. So I'm going to have s minus xs equals 2 plus 4x squared plus 4x cubed, and it's going to then continue on and on and on, with a generic term taking the format of 4x to the n minus 1. And that's just going to continue on and on till infinity. Now, as before, my first term doesn't take that format. So what I'm going to start by doing is considering a partial sum. So what I'm going to do is consider the sum to n terms of 1 minus x equals 2 plus 4x plus 4x squared. I'm going to continue on to plus 4x to the n minus 1. Now, key thing to note here is because that first term doesn't take the format we're after, that's why we have to take it in this form, cut it off at n terms. See if this form just a geometric series straight away, we're in, we just keep going. But in this case, I've got to take it to n terms and then I've got to correct it. So I've then got the sum to n terms of 1 minus x, and I'm going to do the same sort of correction I did before. I'm going to turn it into a 4. So I've got my correct format, so I've got 4 plus 4x plus 4x squared. It's going to continue on all the way up to my nth term, so 4x, but my power is going to be n minus 1. And then I'm going to have a takeaway 2 outside to correct for that. So in this case, my Sn bracket 1 minus x is going to equal this here. Well, that's going to take the format of my sum to n terms, which is a bracket 1 minus r to the n over 1 minus r. For this one, my r, my common ratio, well, that's just going to equal x, and my a is going to equal 4. So for this one, it's going to be a bracket 1 minus x to the n over 1 minus x. But I'm then going to have to take away 2 afterwards. I want to write this take away 2 so the whole thing is one fraction. So I'm going to have that as 2 bracket 1 minus x over 1 minus x. And what I'm going to do is when I take this in, I'm going to multiply at the top bracket to get the whole thing together. So what I'm then going to end up with is 4 bracket 1 minus x to the n, take away 2 plus 2x all over 1 minus x. So I can then rewrite that as my sum to n terms, taking the 1 minus x across, is equal to 4 bracket 1 minus x to the n minus 2 plus 2x over 1 minus x all squared. Now again, what we want to think about is as n tending towards infinity. Well, as n tends towards infinity, what we want is the magnitude of my common ratio, which in this case is x, has to be less than 1. That's what we want for this one. So the magnitude of my common ratio x has to be less than 1 for this to exist. So if I take that, what I can then say is fine, all these conditions are met, so x to the n tends towards infinity. If I then substitute that in, s to infinity equals 4, bracket 1 minus 0, just as we expected here, take away 2 plus 2x all over 1 minus x all squared. And if I sort the top here, I end up with 4 take away 2 plus 2x all over 1 minus x squared. So I can then say find my sum to infinity is equal to 2, and I can take it out as a common factor if I want, 2 bracket 1 plus x all over 1 minus x in a bracket all squared. If you left this as 2 plus 2x on the top, you'd be fine. Sometimes taking out the common factor is more beneficial to you because you might need it later on. And again, for the values for x for it to exist, we know magnitude of x has to be less than 1. So x for this one has to sit somewhere between negative 1 and 1. So there you go. That's a sum to infinity, and that's the limitation we have to put on our values of x and what we have to pick for it to work. The second question was looking for the sum to infinity of this series here. So s equals 1 plus 3x plus 7x squared plus 15x cubed, and so on. First thing we always do again is look at the coefficients and look at their relationship to one another. So I've got 1, if I add 2 I get 3, if I then add 4 I get 7, so it's not the same amount it's gone up by. If I then add 8 I get 15, and I continue on there. Now that's not quite the same style of linear recurrence relation as I had before, because this time un plus 1 is equal to 2 un plus 1. So I've got to multiply the previous term by something, then add it on rather than just adding something onto it. And I'm going to set u1, my first term, equal to 1 there. So it's a linear recurrence relation, so I'm still going to stick with the same style and the same format of my strategy. The difference will come a little bit later though, and you'll see why. So I'm going to start the same way I did before, rewrite it out so that I've got it there to use. So I know s is equal to 1 plus 3x plus 7x squared plus 15x cubed, and so on. And I'm then going to multiply it by x. So I'm going to do xs equals x plus 3x squared plus 7x cubed. And again, it's going to continue on. And then I'm still going to do the exact same step at this point as I did before, which is subtract them. So I'm still going to calculate s minus xs. And in this case, I'd get 1 plus 2x plus 7x squared take away 3x squared, so plus 4x squared plus 8x cubed for the next one, and then continuing on. Now this is where the big difference between this example and the previous example comes into play. Previous example, at this point we noticed the coefficients of all the x terms were the same. So we just had to manipulate it a little bit. Imagine we'd cut it off a set number of terms, look for the sum up to that term, and then let n tend towards infinity. This time we can't do that. It's not going to be quite as easy. But one thing to notice is that this takes the format of a geometric series. Now remember, our general format for a geometric series is un equals ar to the n minus 1. Now a is the first term. In this case, a is equal to 1. R is my common ratio, so it's the ratio of two consecutive terms. And if I look at that, I do 2x divided by 1, so I get 2x. 4x squared divided by 2x, so I get 2x. 8x cubed divided by 4x squared, so I get 2x. So my common ratio in this case is 2x. Now if we have one like this, remember what we are able to do is if we say the magnitude of r for a geometric series is less than 1, we have a sum to infinity. And what we can say is that the sum to infinity, s infinity, is equal to a over 1 minus r. So let's set that condition now. So what we're then going to be able to say is that s infinity bracket 1 minus x equals a over 1 minus r. So that equals a, which is 1 over 1 minus 2x. So I'm then going to divide through by the 1 minus x again, and I'm going to say fine, so my sum to infinity of this series is 1 over the 1 minus 2x times the 1 minus x. But we've got to remember that only exists if the magnitude of r is less than 1. So in this case, the magnitude of 2x has to be less than 1. So for the values of this here, for this to exist, I've got to have negative 1 is less than 2x is less than 1. If I divide through by 2, what that means is negative a half has to be less than x, has to be less than a half. So this series has a sum to infinity, which is 1 over 1 minus 2x bracket 1 minus x, for any value of x between negative a half and a half. If I take it to be a half and negative a half, or any value above either of those two, i.e. the magnitude of 2x is bigger than 1, what that then means is I don't have a sum to infinity. It does not exist. So it only exists under that condition. These are the kind of steps you have to be able to take when it comes to something like this. Always look at your coefficients first. If you get a nice, simple linear recurrence relation of un plus something, great, you're going to do the first set of steps there. If you end up with something times un plus something, what you're going to do is you'll end up with something of this sort of format here, where you get a geometric series here, and you have to work it through with that limit, imposing the correct condition of the magnitude of r is less than 1 with whatever your common ratio tends to be. Bear that in mind when you're working this through. Hopefully, you should find it relatively straightforward once you've tried it a few times.